Okay, is this a green flag? All right, let's start then. Welcome to this session about firmware analysis. It's exactly reverse engineering. And I want to explain here not exactly how to extract information from a blob of data like a firmware image from A to Z, but to present a methodology on how to proceed and how I feel like it should be done. So first, a word about me. As said, I work for a security company in Germany, and I do mostly source code audits, even though I'm also quite fond of network penetration testing and the regular security stuff. And I like to code for open source projects in my spare time, which also means coding for my security team, Uberwall, which presents here the joint efforts for this matter. So what's the plan? Well, basically, this is not gonna be very informative because just like your first impression with some data, I want you to feel like what the heck this is. So first, I think we need to have a global look. And how does it look? We're going to focus on firmwares likely to host an operating system. So I'm not going to talk about drivers, wireless drivers, or the like. And I assume you know how to obtain the firmware you want to obtain. You can read your documentation. You can look for undocumented features of your management interfaces, for instance. Just use imagination, you're hackers, and I continue for doing that. You can also check the vendors' websites extensively, check for unadvertised FTP servers or anything that can deliver files in a way or another. So what I expect to do when I read data is encoding. What I mean is data, the same data can be represented in an infinite number of different ways, which I call here presentation, just like your regular network ISO layer model. And it can be as well compressed and otherwise extracted in any way, such as via a bootloader or any compression algorithm that's doing the job. And I'm going to also talk about file systems, because it's just yet another archiving format. You can just consider file systems to host another number of files and proceed. So about encoding, don't expect anything. I mean, we use ASCII all the time, and it's well-known extensions, but it may as well be anything else. Why not ABCDIC, for instance? If you are reading some IBM software or anything historical or hyped, it may as well be anything. And to prove my point, I will show you how to read ASCII armored data, which is basically another data, but which means something else. So it's the first step. I think encode is a good way to illustrate this point, but I will start with X6 encode algorithm, which is almost the same, as you will see, but still quite simple to grasp. So to encode data into X6 encode, you would group your original data by 3 bytes. If you have not enough bytes, you just consider it zeros. And you split these groups into 4 6-bit numbers. So you can have 4 numbers up to 64, because 2 to the power of 6 is 64. And you do a simple table substitution, with these letters. So say you have the first byte, which is 0. You have a plus. You have the next byte, which is 42 in decimal here. You have an E. And to decrypt it, you just do the opposite. If you have VWXY, it means the original is 59, 60, 61, 62, and then you pack it into groups of 3 bytes instead of groups of 6 bytes, 6 bits, because a byte is 8 bits, as you may know. You encode now, it's exactly the same, except it's faster because the substitution table is quite handily the exact same order as seen is the ASCII standard. So it's faster, and if you want to have a concrete example on where you may encounter this format, if you have some ARM test boards, you will most likely have software uploading the firmware using this encoding. So if you intercept it in any way, or if you get it encoded this way, that's the way to decrypt it. For instance, you encode, encoding goes like this, and you can even have more information than just the encoding. Usually you have the string begin, a permission number, a file name, and then a string end. So you can recognize directly if it's official uEncode format. Now, base64, it's exactly the same, except the character sets vary. So there are lots of implementations using this kind of algorithms. One of them is MIME, which is commonly seen in your mail. BNegs, which was used a lot of time with the Mac. Every time you have a SSL certificate using the PEM format, it's going to be base64. And even your encrypted communications using PGP are using the same algorithms. It's just appending an additional CRC for checksum, for additional check. The output is just the same. So the point is, we have here a pattern. So if you get data, and you see that there's just a restricted set of characters which is used, you can expect that there is some kind of ASCII armoring in a way, or a similar way to encode the data. Just like SOAP does when communicating to web servers, it cannot input any arbitrary ASCII character inside the headers, because if you input like a new line character, it will be another header. So they encode everything this way. This is an example with BNegs. It looks very cryptic, like this, but it's actually just the same algorithm. And we can see fairly easily that it's just readable characters. So the trick is to look for patterns and to identify patterns. Now, something similar but more close to the machine is the Intel X format. If you program microcontrollers or happen to intercept a communication between a microcontroller and the hardware which is going to flash it, it's likely going to be using formats like this one. So it's a series of lines which all start with a colon over there. Then there's the number of bytes in this packet, which can be up to, this is 2 bytes, so that's 64K. The address it's going to load on, 32 bits. The type of packet, the data, because it can be commands or actual data, so you have to check everything before, and then a checksum. So this time, just like with PGP, we happen to find a checksum, which is an interesting challenge as well, because say if you analyze the data as it flows and consider every point to be a potential starting point for a checksum estimation, if you find at one stage the exact state of your current checksum somewhere in the flow, you can determine with a fair degree of relevance that it's a checksum, and so you can delimit, you can separate different fields through the checksum. It's the best example for redundancy inside a data transfer, which is exactly what we are looking for. So X commands just look like this. It's using an even more restricted character set, which means it's even less efficient, but it's easier to read for the microcontroller, and you want it to be uploaded in a safe way. So, of course, a checksum is needed, but it's also going to help us. Now compression. It's just looking I mean, it's the same principle. Data is encoded in a way or in the other. But what we can also interpret from compression formats is signatures, not necessarily signatures from the compression patterns, but signatures from the file formats themselves. So if we take, for instance, gzip, which is used a lot in network transfers as files directly, you have the standard in the RFC 1952, and any gzip file always starts with the same sequence. It's hexadecimal 1F8B, which is a bit short for our purpose. So we're going to have lots of false positives. So you actually also want to check the rest, which is not static, but fairly easy to interpret. It's like a fixed size structure, giving you first here, this is 1 byte with the magic. So it's going to be 1F8B. The compression method, some flags for what's present or not next, a timestamp, the OS that generated the architecture, the file, sorry, and some extra flags. Oh, sorry. Maybe I can add a few comments on this. Yeah. After this header, you may have a file name and a command, which may as well include interesting information for us. And I will illustrate this later with a small demo. Now bootloaders, it's just another potential way for uncompressing data. On x86, you will recognize a bootloader with magic too. It's just 2 bytes as well. But it typically starts with instructions to jump and to initialize stack. So you can also expect the data to include a given set of instructions, and so to identify it really easily. But we'll talk more about assembly later. Unpackers, I just mentioned the bootloader, which is a potential unpacker, of course. But you can also have unpackers in otherwise executable code. And as with gzip, just look for known algorithms, signatures, magic, and potentially play with checksums. File systems, just like gzip, which can have many members, file systems can be considered to be an archive. And as such, we can analyze FAT images just like if they were archive formats, just like with X2 and any file system, any different file system format available. FAT first, it's very poorly documented, unfortunately, because it was developed by one company, bought by Microsoft, not documented for a while, implemented by lots of different vendors. But through the different implementation errors that occurred throughout the time, lots and lots of magic was found inside the file system images. So you can almost always see something like MS-Win 4.1 or FAT, FAT12, FAT16, which are sometimes used to identify the file, the FAT format we're actually talking to, which is not the correct way to identify it. And we have even more magic. Again, the same magic as the bootloaders, some random magic for file structures. And we have even more redundancy than before because the long file names are actually duplicate of the short ones. So if you see the same file names written twice all the time in short sequences, there's a good chance it's going to be a FAT file. CPIO for the Unix world, and more precisely Linux, is both an archive format and a file system. And it's actually to be a very efficient format for RAM disk images. It can be seen in 3 different ways: ASCII R mode with the magic 070707, or in either big endian or little endian. So you have to interpret it in either of these 3 ways. So you have to first identify in which way it's encoded. But for the rest, it looks just like a stat structure. So you're going to see an ID number, permissions, modification time, file name length. You can even get more information on what the vendor wants you to know from this. I mean, you can know when the developers are actually having their shifts from the modification time, for instance. So now I hope you have a structure in mind in how to analyze this data. And if not, if we are still stuck at this point, we can also use simple text or binary forensics. Intuition matters. Strings is your friend. Just look for common usernames, common strings, operating system names, software names. You will see many times GCC appear, for instance, and launch your hexadecimal dumps. And here, I couldn't find any automated tool for doing this, to sort out strings by relevance level and get more information than just analyzing the known data. But I'm trying to write one at the moment, and I'm going to give you a demonstration right now. I'm going to show you a Netgear firmware, which had the particularity to be from the same model as this. It's a wireless router, WG602, which had so far 3 different advisories on Backtrack. One in 2004 with a hard-coded username for administrative access. Another password the same day. And 2 years later, same mistake. So let's have a look on how to identify this. We're going to use first an hexadecimal dump on this. I have no screen here, so please bear with my spelling mistakes. First one, okay. So I'm going to use x60 for this and pipe it through my least favorite pager, but whatever. So what do we have? We have a bunch of random data, but we can already see here the string header 0. Okay, why not? And even piggy. So that's a small piggy inside your wireless router. But for the rest, I can be only sorry there's nothing interesting here, apparently. So let's look deeper. Let's ask strings and be as lazy as just letting this give you more information about it and accept, yeah, this is not really helping much, is it? Strings actually matches any printable characters from 4 characters long. And I can scroll as much as I want, and I still don't see anything relevant. Okay. So now let's use my tool. So I developed a small tool, which is basically trying to match patterns inside files, just like file does, except file will just tell you its data. So the difference is I look from any potential offsets in this file. And what's the result? Okay, lots of false positives apparently. I'm even going to use my latest version, which should look a bit nicer. For your pleasure, yes, with scoring information. So the first match is JZip here, and it's 100%. Which looks quite good. It's at offset 28. So we're going to have a look at this later. And we can see that the rest doesn't look very interesting. Like we have CPIO and JZip signatures, but this doesn't look very interesting. And we can eventually have a look at this one, for instance. So let it be more verbose about it. So it was offset, I think it was, yes, it was this one. So with the compression method advertised is not in a standard. We have some known flags, which is a good start. The date could be actual, even if it's a bit early for this model. And the operating system is not registered. This doesn't look also good. If you look at the next one, the date is from 1964. So I don't know if anyone designed firmware images for this router in 1964, but he was obviously very clever. He should be the next religious personality or something, the next prophet. Anyway, let's have a look at this first signature that we matched. So I'm going to use DD. which is very useful for lots of stuff, including this. So no, not on my executable, on the firmware image, please. And we're going to pipe it to standard outputs, ask it to have a block size of 1 to allow us to skip exactly 28 blocks of 1 byte. We pipe it to gunzip, the regular one, and to the pager. Oh, okay. Thankfully, my pager is escaping escape characters for me. But I think it's going to be easier if we use, once again, an hexadecimal dumper. So we have zeros. And I like it, because it certainly means that the encoding was meaningful for gzip. We have a bunch of, oh, data, okay. More data, more data. Yeah, well, this is not looking any readable right now. Okay, so once again, let's use strings and be the laziest persons in this congress. Okay. Okay. Oh, what's this? Can someone notify anything in this? Oh, I think this is fairly understandable. Linux version 2420. How many advisories on this one? And we even have more information about the software they use to compile it. So we can even have information about the systems the developers used. It's here saying GCC 323 with some modifications.
Can you do a search for IP table?
Oh, yeah. Not matched. What should I look for? Okay. So they use Linux, and we even have some symbols. Of course, we have the strings. You can even see some insults from the Linux kernel, but that's not the point. We already have the source code anyway. So that was for the demonstration. I encourage you to continue at home and have fun. And the lesson is vendors never learn. Now, more identification. And let's go back to full screen for your visual pleasure. So, executable formats first. What do we have? We have mostly portable executable for the Unix, the Windows world, and ELF for the Unix world. And actually tend to be reused because this is very complex to design. It's fairly useless to redesign, considering what's already available and the number of tools which are already supporting it. So I would say it's fairly exhaustive if we just have a look at portable executable and ELF now. And portable executable is actually inspired by Unix COF and still compatible with MS-DOS 2. I'm saying 2. It's not a spelling mistake. And if you say, but Windows is not portable, why is it called portable executable then? Well, Windows is not just XP or 2000 or MS-DOS 2. It's also Windows CE, and Windows CE runs on a number of platforms, including big engine platforms, just like NT4 was also running on alpha machines. And it's used for not just executables, but also libraries, device drivers, and even screensavers. So the file format is looking like this. You have first an MS-DOS 2 header, which is nowadays waste, I think. Then you have more waste. You have some information about the vendor. Then you have finally the offset to the actual header. Then you have more waste, a stop program to say this program cannot run. More waste. And finally, what we are looking for, the actual header with the extra stuff. The actual MS-DOS header is looking like this. So we have magic. It says MZ here, always, whatever happens. And you can also look for this program cannot be run in DOS mode because the compilers always include this by default. So I don't know any, I mean, if I were a developer for a company, I would not bother remove this. So I guess nobody does. So look for this and look for this offset here, which tells where to look for the PE header, which is looking like this. We even have more magic. This is always 50, 45, 0, 0, 0, 0. This is always 0. This is always 0. You can also look at this offset, which is meaning this is a file for i386 platforms, P32 executable. The linker used was version 7, which is appearing here. So you can guess which version of Visual Studio they used. The entry point is here, if you want to run it inside an emulator or further debug the application or disassemble it. And this is more version fields. One is for which Windows version is required to run it. Here it's Windows 94. And with which version of Windows it was generated. 5.1 is Windows XP, if I'm correct. So that was for PE. Now let's have a look at ELF, which looks almost the same, except it's just simpler. It's just a series of sections. And it's even easier to spot because it says directly in the first 4 bytes, 127 decimal and ELF. Just a list of sections, a program header table, section header table, strings packed together, fairly easy to recognize. And the best way to know about this format is actually to read the C definition. So if you're familiar with C source code, this is the way you're going to be reading it more efficiently, just like PE. It's a pain to do it manually, so write tools, use tools, and look for this kind of information. Try to fill it and see if it makes sense. Here you have 16 bytes just about metadata, the magic, for the first 4 bytes. And you have even more information here about the machine use, the versions, types, more flags, entry points, number of sections, which is also some kind of redundant information. So with a very efficient program and lots of computing power, we could probably guess it, even if we didn't have this format, this definition, I mean. Okay, now let's skip to some more low-level stuff with some processor architectures. I will speak a bit about x86, of course, because you all have one, I think, even in your brand new Macs now. And if you happen to be a gamer or using circuits boxes, it's also all running x86. It's only little endian, so when you read, if you see some binary data which is longer than 1 byte, reverse it and see if it makes more sense. We know from the bootloader slide, the standard boot process, 512 block with a given signature and some stack initialization instructions, which are also present in the FAT file format, because it doesn't start after the bootloader, but actually inside the bootloader, because every partition is bootable. And there's not just one way to boot an x86 machine. Some x86 machines have firmwares for years now, just like Cobalt racks in your provider's former data centers. And now we have open firmware and new stuff coming. We can identify it directly from the assembly. You can see a fair amount of instructions which will be looking like this. 5589E5, which is stack code when you change from function to function. And when you leave the function, it's going to be C9, C3. So if you look for just this magic and look for the patterns in how it appears, how sparse, and like since the next function should start after another one, this should be right before this all the time. And if you happen to see data containing this pattern, you can guess that it's x86 assembly with a fairly good estimation. Now ARM, or Acorn RISC Machine for the full name. It's used in lots of embedded systems. I even have one in my pocket here. I think so, yes. Nosaurus, it's a complete machine with an ARM processor. And of course, it's running Linux and has few more images downloadable, and you can replace it and play with similar hardware. just like some game consoles, maybe, or your phone. It can be little or big in the net wheel, so don't expect anything regarding the encoding at this stage. Try to reverse anything from big to little endian when you guess something longer than 1 byte. And look for fixed type instructions. Every relevant data for assembly level code should be aligned on 32 bits, except with the new opcode system, which is called ZAMP, and which supports 16-bit opcodes, which then may be aligned on 16 bits and not necessarily 32. MIPS is fairly similar to recognize. It's used in some workstations, just like the old SGI stations. It's found in some modems as well. And all the newest, no, not the newest, but fairly new game consoles. It can run 32 and 64-bit instructions. Once again, it's fixed size opcodes, which can be a waste because you don't want really one instruction to take 8 bytes, but just like ARM, it's packing instructions into one, but still it's aligned. And it can also run into little or big endian at will if you reboot it, so don't expect the endian to be always the same. PowerPC, now for the recent game consoles, and also your legacy Apple computers, X terminals. You can also play with such firmwares and look at how it looks like. Operating systems now. Besides the very famous ones like Linux or Windows, you may want to play around with Cisco iOS, or you may find into consumer markets some real-time operating systems, just like QNX or VxWorks, which I'm going to introduce now because they're not very well known for the regular, for the public. It's a Unix system, which has a true microkernel design, which can be very interesting for the OS developers among you. You can also run it on your PC. You can download images and see what it looks like. And it's getting even more interesting now that Cisco is using it for their new operating system on their newest high availability routers. It's actually running QNX even if it's iOS. VxWorks is fairly similar to QNX, another real-time operating system. It's used into some space stations, even space satellites, not like your Sputnik thingy, but real satellites. And in your regular hardware, if you have a Linksys WRT, it may run under VxWorks instead of Linux, depending on the revision you have. Some DVD recorders use it as well, some digital cameras, modems, and even some printers. Some printers actually run full-time, real-time, full-featured Unix operating systems such as VxWorks. So just have a look at anything. It can run an operating system with a complete TCP stack and make some noise on the network. Now, if at this stage we are still stuck because the vendor did a really good job or it's ciphered in a way and not just compressed or twisted, we can consider ciphering and deciphering. By definition, encrypted content is looking random for the eyes. Not even strings can tell you anything about it. But again, we may have some clues somewhere about it because as the rest is designed by humans, humans make mistakes. Perfection is really difficult to achieve. And as such, every algorithm may reveal some signatures or patterns when you look at it in a different way. It's not my specialty, but I know that there is encryption and encryption. And if you look at embedded hardware, you may not have as much power available as for your new Core Duo laptops. So don't expect the crypto level to be too high. It can be, but it's worth a try. So if it's not just a pure algorithm, just like XOR, try it. And if it is, it's certainly unpacked at boot time And so the logic is there, just written in assembly language. So try to reverse it. Try to reverse just the bootloader, or what looks like the bootloader. If there is a key, it's certainly there in the clear. Unless with the newest DRM devices, but I don't know if there are so many here, and some implementations are just broken or not using them. If you want, however, to have a look inside the hardware, you can do it also, but you can expect to have to save almost €1 million to get a microscope powerful enough. But anyway, you can get some cryptography books, or actually ask Dan Kaminsky. He's been doing some work recently about how to draw pictures from data, any kind of pictures. He's doing some very nice abstract paintings, and seriously, it helps. We can imagine recognizing, for instance, the same image encoded in GIF or JPEG instantly, and then recognize other images encrypted in GIF, in opposite to next to JPEG versions, because the patterns, if you draw it in a good way, will just stay coherent for GIF images and JPEG images. So if you can determine patterns for, say, a or blowfish or serpent or whatever, maybe you can guess how it is actually encrypted. Of course, you don't have the key yet, but still, it helps. What is this penguin doing here? Okay. We'll have a look at encryption and encryption, actually, because there are two main ways of doing it, by cipher chain blocks or purely block cipher. Let me explain. In the first case, the key is the same as in the second case, but the data is not randomized by or influenced by the previous block, which means that for given input data, the encrypted data is always the same. So even if it doesn't look like a penguin, unless you look very closely, you can see it. You can guess that it's a penguin in steganography or encrypted in a way. And you can apply the same principle for regular data. If you recognize patterns and it looks like, for instance, a fat record, but it doesn't correspond to a fat record, try to modify it, correlate, graph it, and see if it can not exactly be a fat record from with an encryption in any way. And now for the last part, we'll tell a bit about disassembly and how to emulate the images we just uncovered, and why not debug them. Disassembly software, I would recommend using an ASM for x86 or the GNU binutils for the rest. And for Windows platforms, you may know about ODDBug and IDA Pro already. IDA can not just disassemble Windows executables, but also all kinds of architectures and operating systems. It's not free though. And there are rumors that it may be removed from the market sometime soon. Now, emulation. It's getting really looked at currently. I see every day new announcements of new emulation software available. And you can already emulate pretty much everything that has a processor, a memory, and a process counter, actually. So for x86, you have lots of different choices. I'm going to explain just after this slide differences between the two major ones. PAPC for PowerPC. MIPS has a high number of emulators available. You can also play games if you want. You certainly know MAME. And there's also a number of emulators for Cisco routers. And I'm running out of space, but there's really plenty. So Box, free software and designed for operating system developers. which means it can also be useful for us because it works with GDB. So you can actually get stack traces and get some runtime information whenever you want. Fetch runtime memory emojis. It includes also on top of that its own debugging system, and it's going to tell you if the current instruction running is looking like an actual one or not, depending on the status of the registers or the processor flags or anything. On the other hand, QEMU can run in native mode faster, but you cannot analyze just as much because it actually, I think it vectorizes instructions. It creates instructions from the original image and directly runs it in memory. So you cannot really hook into it unless if you run into the other mode, which it also supports. And not like Box, it also supports Spark, ARM, and MIPS architectures. So it can be very useful to emulate, debug, and analyze firmware images besides x86. And it also works with GDB now. No, I'm almost finished, sorry, with this talk. Wikipedia was a very good help with this research. I think you know how to use the search button on Wikipedia. There's articles on pretty much everything already. The NetBSD page about emulating the ports is really complete about how to run software from any processor available, something like 30 or 35 different architectures. You also want to fetch the assembly reference books and why not the specifications parts of your user's manuals for the hardware you're currently looking at. Look for any clue, use Google, use Wikipedia. And I thank you for your attention. I thank also my company for giving me some spare time to do this. Check out our website. I just released my tool yesterday. It's not complete. It's not as, it doesn't go as far as I wanted yet. But if you want to contribute, you're welcome. Just drop me a mail. Stay tuned. And if you have any questions, just ask anytime. Thank you.